continue with indexes. So in the last class, I kind of spoke about what indexes were. So they are files, just like your data files in the databases, all these tables. Every table has indexes connected to them. At a minimum, every table has at least one index, which is the primary key index. And so these indexes are also files that are stored, they're persistent data that's stored with the tables. And the advantage of indexes is that they are orders of magnitude smaller than a file. So if you want, when you have queries where you're trying to search a large file, what you can do is you can upload the index into main memory. It's small enough, and you search the indexes, and indexes are data structures where it's very easy to search. So they are hashes or B trees. And so you search for the key in the index, and then the index points to where the row is stored on the disk. So then you just have to upload the disk blocks that satisfy the query. So that's what indexes are, and that's the advantage of indexes. And if you didn't have indexes, databases wouldn't exist because they would be way too slow. So there are different kinds of indexes. And the first one I started speaking about was the primary key index. And so one of the things I mentioned is that on the primary key, if you are storing the data on the disk, where it's sorted by the primary key, then you just need to have a sparse index. So by sparse index, I mean the number of index entries are much lower than the number of tuples in the table. So number of index entries is lesser than the number of tuples. So for example, the one out here, if it's sorted by that 1, 2, 3, 4 by, let's say, this number or department number, then you can have the index just pointing to, index department number 1 that is on disk block 1 and department number 11 on disk block 2 and so on. On the other hand, if the table is not stored in sorted order by primary key, then you would need, you have to store all the 1, 2, 3, 4, you'll have to store every one of them. So then it's called a dense index. So if it's not stored by, so if it's stored in sorted order by primary key, then it's a sparse index. So if not, then you have a dense index. So that's the primary key indexes. And then the next type of index is the clustering index. So sometimes, database designers or, the people who are implementing on the, they may decide that, there are a lot of queries on the employee table by department number. I mean, often a lot of queries are based on employees in a particular department. And since there's so many queries that, revolve around department number, why not store the file in sorted order by department number? So instead of storing it by social security number, physically store the file sorted by department number. So a department number is not a key. So those are called clustering indexes. So tuples are physically stored, sorted on a non-key attribute. And like I said, a good example is department number in employee table. So when you have clustering indexes, they are sparse indexes because you are storing the table sorted by that attribute. So these are sparse indexes. Um, so, so again, this is not, this is something that the person, when you do a database, the administrators and all, when they're trying to figure out how on the back end, on the storage end, how to store the files. So I have to really say, when you do databases, if you are working as not as a database programmer, but you're working on the back end of databases, you also have to really work very closely with the storage part of it, the physical, the low level end, the operating system part of it, because if you have no awareness, or if you don't really decide how things should be stored on the physical end, then the performance, it affects the performance on the that you're going to see at the other end, because because database files are also large and they're stored on disks, which are the bottleneck. So therefore, it's very, very important. Any kind of improvements you make at the disk end, you'll see magnitudes of improvements upward. So, so at that end, you have to be very good, even at the systems level, at the low end, not just the upper end. And I'm not talking about people who are writing application programmers. I'm talking about the database, people who are dealing with the administrators and all at the back end of the database. So then the third type of index is the secondary index. So this is when you build indexes on candidate keys and foreign keys, because so many queries are based on candidate keys or foreign keys. So I mean, if you look at queries, so many queries, they kind of where you join tables and stuff. So they really use these foreign keys. So these are always dense indexes, because you're not storing it's sorted on these keys. And then the last one is the multiple attribute index. So for this one, I'm going to show an example to explain this index. So let's say you have this query, select star from employee, where D number is equal to 5 and salary is greater than 50,000. So this is a query where you are looking for employees in Department 5 who earn more than $50,000. So suppose suppose this is a very common query that's generated. So you decide that, okay, it's worth having an index on department number and salary together. So you do an index on D number and salary. So it's a multiple attribute index. And this can really speed up performance. So I'm going to explain this part with an example where you can see that happening. So I'm trying to see, should I do this one? Yeah, it's a little complicated for me to draw for this particular query. I want to show something where I want to show you the lower end of it. I want to give an example. So it's difficult to show it with, with this particular multiple attribute one. So I'm going to do a simpler example than this one. So let's do this following example. Okay, so I'm going to look at the department table. And suppose we have the following DNOs in the department table, department numbers. We have 2, 3, 5, 7, 23. Okay, so I want to just show the whole thing now at the disk, what it looks like. So let's go and zoom down to the disk and see how this is stored on the hard disk. So we have, okay, so this is the disk. So this is the department table on disk. Okay, so this is a small table. So we have, suppose we store it on 5 blocks. So we have block 1. So block 2, block 3, block 4, and 5 blocks. Okay, so these are just disk blocks. So we have disk block 1, disk block 2, okay, so we have 5 blocks, and let's say we store 2, 13. Okay, so this is the way, let's suppose that this is the way your file was stored on the hard disk. You have 5 blocks, and each block stores 3 rows. And I've shown the rows. So let's make, so this is the actual department table on disk. So now I'm going to do the index of this table. So it's a B tree index. So we have a B tree index. So we have, I just want to do one, fully so that you get an idea. It's a tiny example, but it's better than none. And I think that if you can visualize things, it's a lot easier to understand. And then at the bottom, we have 1, 2, 3, 4, 5, 6. So we have, so to move it a bit, I ran out of space. Okay. Okay, so we have, let's say 2, 3, 5, 7, 11, 13, 17. Okay, so we have this B313. Okay, so I'm just drawing the B tree index for this particular file. And then all of these will point to the block that it is. So 2 is stored on data block 1. So 3 is stored on data block 2. 5 is on data block 2. 7 is on DB3, and so on. So each of these will point to where it's stored on the hard disk. So let's say this is what the department table looks like inside on the disk, and the B tree index that's pointing to it. So suppose you give this particular query, select star from department where D number is less than 7. Okay, so suppose this is the query that the users generated. So I just want to show how indexes affect the performance. So, so first, let's look at the case where there are no indexes. So if you have no indexes on this department table, and you're giving this query select star from department where D number is less than equal to 7, you would have to search all the disk blocks. There's no other way of knowing, because they're not stored in sorted order by the department number. So in this case, you have to access all the 15 tuples, and you have to access all the 5 disk blocks. So, and again, remember, this is a small example. If this one had 10,000 blocks, you would have to access all 10,000 blocks. So if you have no indexes, you have to access all the 15 tuples and access all 5 disk blocks. And here now, if you have an index on department number, like we have shown out here, so where D number is less than equal to 7, you just have to actually go look here. And then that means you have to go down here, and then it's less than equal to 7. So the first one's here. So those are the 4 you have to look at. So we have, you have to look at 2, 3, 5, and 7. So all you have to do if you have an index on D number is you have to access 4 tuples. And if you look at the disk blocks, I think they are all in disk blocks 1, 2, and 3. So, so you have to access 3 disk blocks. For the 3 disk blocks. So let's assume that you upload only 1 block at a time and you access the disk. So that's the difference between having no indexes and having an index on D number. And let's suppose that we had actually stored it in sorted order by D number. So suppose department is stored order. So suppose you have a sparse index on D number. So in this case, we would be storing it as 2, 3, 5, 7, 11, 13. 29, 31, 37, 41, 43, 47. So Okay, so here we have 5 blocks again. I mean, just because you did in sorted order doesn't mean it'll be. So block 2, block 3, 5. So in this case, it would be, you would be accessing, again, you would access 4 tuples, but you would only be accessing 2 disk blocks. So I just wanted, I know this was just a very, very small example, but I hope that you can, you can kind of extrapolate it to something really large and see the impact that indexes can make. So if you have any questions, please jump in.
Just if I'm understanding correctly, only one index can be sparse because it can only be sorted by one element, right?
Yes, only one index is going to be sparse index. So so it's really most often it's by primary key, but a lot really depends on like you said, if you find that a lot of queries are by department number on the employee table, then it makes sense to actually build the index sort it on department number. But yes, only one. The physical, you can only really sort it by one. Only one index can be sparse. All the other indexes are going to be dense. So yeah, so let me give you a few other questions on indexes. So let's look at the next one. So by the way, all of these examples are really questions of the kind that I would give on the final exam, because I'm not giving any assignment on indexes. So I just want to make sure that you kind of understand, because I don't ever ask questions that ask you to define things. So it's all going to be stuff like this. So I'm going back to so I want to go back to the previous example, the multiple attribute example that I did. So it's too large for me to actually draw, but here I still want to give you an example and try to show you the difference between having an index and not having an index. So select staff from employee where D number is 5 and salary is greater than 50,000. Okay, so let's assume that there are 3,000 tuples in employee table. So there are 3,000 rows in the employee table. Suppose out of those, there are 100 employees in department number 5. And let's suppose that there are 300 tuples of employees who have salary greater than 50,000. And let's suppose that you have and out of these, let's assume that there are 10 tuples. It doesn't look like an arrow. Suppose there are Suppose there are 10 tuples. So there are 10 employees who are in department 5 and have salary greater than 50,000. So I'm giving you all this information. So I want you to look at the following. I'm going to give a bunch of questions and I would like you to attempt to answer them. So how many tuples accessed? Okay, so how many tuples are accessed? So 1. If there are no indexes, if there's an index on D number, there's an index on salary, there's multi-attribute index on D number plus salary. So I just want you to write down this and then I'll go over that. So I'll give you a couple of minutes.
Could you maybe give a small example on how the multi-attribute index works if for like the B tree or the hash table?
Yeah, so with the on the multi-attribute index on D number per salary, so there will be so there'll be an index on D number, which again points. So I mean, you have to draw this. I'm trying to see. So they are. So you have I mean, it's a different data structure. I mean, they're using a combination of the B tree data structure. So I think in the textbook, if you look, I think there is an example of that. I think that's better because there's a diagram. They've shown these indexes in a lot of detail with the diagram. So just take a look on that one.
But having a multi-attribute index isn't equivalent to having an index on each of the attributes, right?
On what? On D number and on salary separately?
Right.
Yeah, it's not the same. It's a different type of index. So the data structure it's a B tree, but it's kind of a level. I find it difficult to explain, but like I said, because you have to draw a diagram on this, and in the textbook there are diagrams of these indexes. So there are all kinds of data structures actually for indexes. They're layered, and it's a whole different area, all the data structures for indexes. So anyway, for this one, for the no indexes, you have to search everything. So since there are 3,000 tuples, you have to search all 3,000. So if it's an index on D number, then you have to, I mean, you get 100 tuples with D number is equal to 5, and then you have to search them. So you just have to search 100 in this case, because you'll get 100 with D number is equal to 5, and then you search them for, 100 tuples, and then search for salary greater than 50,000. So you're searching 100 tuples. And then for salary, you pick the 350,000 tuples, and then you search for D number. On the other hand, if you have a multiple attribute index on D number and this, then you just have 10 tuples. So you can see the difference when you look through all this. And then how many disk blocks access, that's not something you can answer because I didn't draw. That's why I said, since in order to figure out how many disk blocks have been accessed, you would have to know the setup on disk. You would have to have some, you'd have to draw something like this, and you have to know how things are placed on the disk. Since I have provided no information, like I said, it's too complicated on this one. So you cannot know how many disk blocks were accessed. So I hope you understood how the answers on these questions. Yeah, and for a multi-attribute, I just on the fly, it's difficult for me to draw a diagram, but I'll go back and look at the textbook, and maybe if it's simple enough, I'll try to draw one on the next class, if it's simple enough, because some of these things are a bit complicated. In general, I have to say that indexes come with a cost. And you can imagine, right? Because every time you insert, delete, or update a table, you have to update the indexes. So they are expensive. So don't just randomly make indexes on tables thinking that your performance is going to be great. You have to be careful because you should choose your indexes wisely. So normally database programmers do not have permission to build indexes. These are done by on the back end. You need permission. You need access permission to build indexes for that reason. So based on the type of queries that people normally ask, you build indexes. But don't just randomly build indexes on everything. So sometimes multiple attribute indexes and all those are expensive. So yes, you only have to pick up 10 tuples, but is it worth the expense of having such an index? May not be there. So in general, you build indexes on, like I said, primary keys and foreign keys and things like that. So on the company database, if you wanted to build an index, I'll just give you the commands that I used. So building an index is create index, and then you give the index name. On, oh, I'm sorry. I just want to create index, index name on table, and then you give the table name, and then you write down the attributes on which you want to build the index. So that's the command for building an index. And if you want, you can also specify, I think default is B trees, okay, though I'm not completely certain. So using B tree. And I think on primary key indexes, the default is hash. So again, I really should have checked up. Last time I said I would check and I forgot about that, but you can look it up. So it's usually a B tree or a hash. So for example, I could create an index. So I could say create index, let's call it ID number on employee DNO. So I'm creating an index called ID number on the employee table on department, on the attribute department number. So once I do this, this index will be created. So it's a file that's going to be stored in the database. So if you want to see all the indexes on your company database, you can use the command show index from, and then you give the table name. So for example, I would have, I could say show index from employee. And that will show me all the indexes that are there on the employee table. So again, like I mentioned in the last class, is that most databases will build indexes on primary keys automatically. So you don't have to build it. It's done automatically. So it's done by default. But sometimes if you want, you can build it on, so if it's not already there, you can build it on foreign keys and on candidate keys. So on unique is candidate keys. And on foreign keys. So I'm not sure that they do it by default all the time, but they don't. Sometimes it's a good idea to have those indexes also built. Okay, so then let me just do another example on, with a question using indexes. So this time I'm going to use a query that is joining two tables. So we have, so this is a join query. So select pname, dname from Okay, so this is a query, select pname, department name from project and department, where manager social security number is 1234 and department number is equal to department.d number. So this is the join query part, and then you have this. So, and suppose you are given that, so you're told that the department has 1,000 tuples, project has 5,000 tuples, and suppose you're told that the manager's social security number 1234, there's only one tuple. So the manager, so there's only one tuple with this. So we have manager SSN is equal to 1234. So suppose you're told that this guy manages department number is equal to 5. So he's only managing, or she's only managing one department. And this department has the 10 project tuples with D number is equal to 5. So you're given all this information. So I'm then, so these are the questions I'm going to ask. So we have, so how many tuples are accessed in worst case? So in the worst case scenario, how many tuples are accessed when one, you have no indexes. Two, when you have an index on MGR, SSN. Then 3, you have an index on project.d number. And 4, you have 2 indexes. So it's not a multi-attribute index, but you have these 2 indexes. You have 2 indexes. You have an index on MGR, SSN in department, and you have an index on project.d number. Okay, so I want you to try this out. How many tuples are accessed in the worst case for these 4? So let's look at the first one, of course. When you have no indexes, you have, so this is a join query, and you are told that there are 5,000 in project and you have 1,000 in department. So you got to access everything. So you're going to have, in this case, 6,000 tuples, because you're going to have, let me just move this down. No. Because you're going to have 1,000 in the department table plus 5,000 in the project table. So that's how you're going to get 6,000 if you didn't have any indexes at all. So if you have an index on manager social security number, so anyone did what are the, can anyone just give me their answer? What did you get for that? How many tuples would you have to pull up if you have an index on manager social security number? Anyone wants to volunteer?
I got the 1 for the manager and then the 5,000 for the projects.
Yes, you're right. So it's 5,001.
Yep.
So we have, good. So that's the thing. So you're going to get 1 tuple in department with and you're going to have 10. Oh, what did I say? 10, 5,000. In project to find the department number is equal to because it's the worst case, you'll have to anyway look through everything. So to find department number is equal to 5, since you don't know where all you're going to find tuples with department number is equal to 5. And then the project D number is similar to the previous one. Oh, sorry. So I just want to move it down a bit. Okay, so we have, so this one would be 1,000 for department tuple. Okay, so what, yeah, just can anyone volunteer the answer for index on project.d number? How many did you get? Anyone?
1,005.
1,005. Why is it 1,005? Why not 1,010?
Maybe I did it wrong.
I mean,
oh,
you must, the 1,000 part is correct, right?
5.
Yeah,
Yeah.
it's department number is equal to 5, so it's 10 project tuples. I can see the confusion there. But it's 10, so it's 1,010 actually. So you did get it correct. You just
Yep.
it's 10 there, so it's 1,010. So there are 1,000 in department for searching for manager. SSN is equal to 1, 2, 3, 4, and it's a worst case. You have to search all 1,000 before you find it. Maybe the last one is the one you find it, and then you have 10 project tuples. So you search that to find manager social security number is 1, 2, 3, 4, who has department number 5, and then you look at 10 project tuples with this. And then the last one, when you have two, so we have, so let me just, since it's almost 10 o'clock, let me just write it down. So we have 11 out here because you do 1 from department for manager social security number. And then you have 10 from project for D number is equal to 5. So you have a total of 11. So, do you understand this? This, because I mean, these are the type of questions I would be giving for the, fine. So that brings me down to, I know it's 10 o'clock. So we already have 11 quizzes, and that's pretty much it, what I do for most classes. But this year we have an extra week. I think it's because I didn't have a midterm exam, so we have 1 extra week for that. So I'll give you 12 quizzes. I think it'll be really helpful to do some questions on indexes and constraints and triggers, because there are no assignments either on that. So, but instead of giving it on Wednesday, because I haven't finished indexes yet, I'm almost done, but not quite done. I'll have the quiz on Friday. Is that okay with the people who are attending? I mean, is that okay with you if I have the quiz on Friday this week?
Yeah.
Okay, so I'll have it on Friday. Oh, did someone say no?
No, that will work. That will work.
Okay. So I'll have it on Friday, and I'll give it from all 3 topics. And I'm going to allow you to drop 3 quizzes instead of 2, because normally it's 11 quizzes. I'm giving you 12. So I'm going to allow you to drop 3 quizzes, because I do understand this is getting to the end of the semester. So everyone's really busy with so many other classes. But I'm also allowing this because I was just looking at the grades for students. Most of you are doing really well, but some of you are, because you stopped doing quizzes and stopped submitting assignments, you are not doing well. Now, those of you who are going really low, and I'm talking below 50%, I think it's kind of really low at that point. I don't know if there's any hope at this point, but if you are, let's say, close to the 50% ballpark, so not the ones who are below 40%, if you're falling below 40% at this point, don't bother with this class. You're going to fail, so focus on the rest of your classes. But if you are somewhere close to the 50% margin, my courses marks you as F, but I might still scale you up if you can, get through, because anyway, you get half the credit if you just take the final, then you just have to go a little higher than that. So all I'm saying is if you are somewhere close to 50%, please don't, I mean, you might still pass the class, maybe with a D minus, but you might still pass the class. So so I'm really giving this extra quiz more for those people who are, you know, at that close to the 50% thing, you know, it just take the quiz, you know, because I've noticed a lot of people have stopped taking quizzes and stopped submitting assignments. So just go ahead and do it. The final exam is going to be really more on the second half of the class. In fact, it's almost entirely going to be from the second half. I'm not really going to ask any questions on relational algebra because by now I think most of you might have mapped that out of your head. So, and even SQL queries are really more going to deal with stuff we're doing in the second half of the class, you know. So yeah, so I'll give the last quiz on Friday. And the last assignment is due today. So, so any questions?